So at some point, soon, probably next class, but soon, you are going to be asked to find a third vector so that when you combine the two vectors you're given in the beginning, so you're going to be given two vectors, and then you're going to have to figure out the magnitude and angle of a third so that all three vectors will cancel each other out and make 0, or what they call the null vector. But whatever. But we're going to actually have a physical activity, a lab that you're going to have to do where you're going to have to figure this out, and we will be able to determine very quickly, and sometimes dramatically if it doesn't work out, whether or not you correctly found this vector. So I'm basically handing you the procedure for that right now. So pay attention. Now what I would do is I would pause this video and read the stuff that's on the screen right now and check back with it periodically so you can kind of see the steps involved come to life when I do the example. So if you read I would skim the steps, see what they look like. Even if you're not sure what I'm talking about, then go back and forth between the example and go back to these steps and see, if they make more sense at that point. Right, so pause the video and read the stuff. Okay, so hopefully you've read the stuff, and now let's go on and look at an example. Okay, so we have two vectors, and I've deliberately, in this case, given the vectors with their angle in two different ways. Here is just the angle, and here it is as a reference angle. And so when we go to sketch them in a moment, we'll just clarify, make sure we understand what we're talking about there. But these are our two vectors. And you'll notice that the magnitude of this one is larger than the magnitude of this one by more than double. I don't know about 3 times, but let's see how many times larger. 5.4 divided by 1.7. About 3, yeah, a little over 3 times larger. Okay, so that's good to know. So that the magnitude of vector 1 is equal to approximately, squiggly equals means approximately, 3 times the magnitude of vector 2. So that would give us an idea. Okay. So the first step is to sketch the two vectors. So here we have a piece of graph paper, a grid system on it. And we're going to keep in mind that, let's do this. So we are going to make, interestingly enough, there's a lot of ways you could do this. I think we're going to use, I'll use the red. So as a idea of how long something is, this is 1, 2, 3, 4, 5.4. So this represents a length of about 5.4. This is going to represent, the next one is going to represent a length of about 1.7. You'll note that's the size of our two magnitudes. Now, roughly speaking, that'll work. So, let's put our two vectors on here. Let's see. What colors do we want to use? So we're going to go here. We'll do one of them in blue. And we'll do one in red. There we go. So the first vector is going to be the 5.4 at 325 degrees, I believe. Pardon me. There we go. Yes, 325 degrees. So 325 degrees is going to be somewhere, let's see, this is 270, and halfway along between 270 and 360, which would be all the way around, let's see, that's going to be 315, so about another 10 degrees past that. So I'm thinking that our angle is going to be somewhere in that vicinity. So let's draw our angle. Let's draw our vector. So we'll do this one in blue. Well, yeah, we'll do it in blue. Now remember, it's going to be 5.4 long. So it's going to be, let's see, about, do this right, it's going to look like that long. Let's see if I can move that to here, and then 1, 2, 3, 4, 5.4 is a little more. So this is going to be the tricky part, is getting this one correct in the length. Because if you have paper, it's much easier than what I got going on here, but we'll try it. So let's see, 1, 2, 3, 4, 5.4, about like that maybe. We'll go with it. It's a sketch. So there's one of our vectors. The other one is about 1.7 and is at an angle of 40 degrees third quadrant. That means, let's see, here in the third quadrant, if you're not aware, this is the first quadrant, second quadrant, third quadrant, fourth quadrant. Oh, there we go. Fourth quadrant. So in the third quadrant, when they say 40 degrees in the third quadrant, they're talking about a reference angle. They're talking about, let's see, well, this here would be 45 degrees as a reference angle. But we want 40, so we really are looking for something just a touch, somewhere in that direction. But our vector is not going to be very long, because as you'll note, its magnitude is almost a third, or a little less than a third, of this one. So we'll do this one in red, and we will put it just a little guy, about like that. That'll work. So here are our two vectors. And you're welcome to use, obviously you're going to have to use pencil and paper to do it, and in fact rulers wouldn't be a bad thing either. So the next thing we're going to do is we're going to add those two vectors together graphically, just to get a feel for things. So there's two methods, tip to tail or parallelogram method. I'll demonstrate both real quickly. Parallelogram method, literally just imagine a line, sketch in a line that is parallel, so this black dotted line is parallel to that, as best as I can get. And if I have to go back and resketch it a little bit, I will, but there we go, it's about parallel. And then this black line is going to be parallel to this side, here. Not bad. I'm thinking this can come in more, like so. There we go. So that one's parallel to the blue side, this is parallel to the red side, and I've created a parallelogram. The reason that's important is our resultant vector, our answer when we add those two vectors. Let's do that one in purple, make it solid, is going to be a vector that starts here and goes to wherever those two met, right there. So that is your resultant. Now, another way to get that purple vector would be to do this. So let's set it aside. We'll come back to it. The other way to do it is this, is the tip to tail method. So what I would do is sketch the blue vector that you see there. Just sketch the blue one. And then take the red one and draw it starting at the tip of the blue. So as if there was a coordinate system here with an x and a y-axis, and sketch the red vector down like that. And then wherever you end up is where you're going to draw this vector. Notice it's the same either way. So let's put this guy back. So the sum of the blue and the red is the purple. Ooh, look at that color, blue, red, purple. Well done. So ultimately, though, that purple vector is not the vector that's going to cancel the other two out. I want the opposite of this purple vector. I want the exact same length, but in the other direction. So I want something that looks like, let's do this. Clone it. I want something in the exact opposite direction, same length, but pointed in the exact opposite direction, like so. That's my guy. That's the vector I want. This vector here will cancel the red and the blue. In fact, I'll remove this other one, get rid of some of the scribble, and point out that if you added when you add all these three vectors, you will get 0. They will all cancel out. And so we're going to figure out this one. So now, the reason I sketch is now I expect my answer to be in the second quadrant, to be roughly as long as to be longer, not shorter. Sometimes two vectors might make a small vector. In this case, it's a pretty long vector. And the angles, I'm guessing, just based on my drawing, closer, somewhere between 90 and 135, which would be halfway through here. So maybe somewhere in that neighborhood. But at least I have a feeling for what my answer is going to look like. Okay. So the next step. So we've done, check, we've done the sketching part. Now we're going to, first step next, break down these into their components. So, let me do this. Oh, we'll do it. I'll move this to the next slide. Okay. So next we're going to do is break these into their components. So we're going to take V1 and find its x and y components. Now remember, the x component of any vector is the magnitude of the vector times the cosine of its angle. And the y component is the magnitude of the vector times the sine of the angle. So for the V1 x component, it is going to be the magnitude of V1, 5.4, times the cosine of a 325 degree angle. V1's y component is going to be the magnitude, 5.4, careful, times the sine of the 325 degree angle. Take a moment, see if you can figure out what those are. Maybe pause the video. So I get an x component of 4.423 newtons and a y component of negative 3.097 newtons. Now, notice the y component automatically came out to be negative, which makes sense because you'll remember that vector is down here in the fourth quadrant where we have positive x's and negative y's. Our other vector, well, here's the thing. They're giving us a 40-degree angle in the third quadrant. There's a couple options here. You could use the 40 degrees. But if you do, nothing wrong with that, but if you do, you have to remember that in the third quadrant, because that 40 degrees is not going to give you any negatives if they should be there. And in this case, if you remember, third quadrant, both the x and the y are going to be negative. So if you use the 40, your calculator is not going to tell you that. So you got to know that. You got to know what quadrant you're in. So that's going to be 1.7 times the cosine of a 40-degree angle. So I go 1.7 times cosine of a 40-degree angle, and I get 1.302. But I know it's in the third quadrant, so I know it has to be negative, so I assign the negative to it. And I do the same thing for the y. So vector 2 y component is going to be 1.7 times the sine of 40 degrees, but account for the fact that you're in the third quadrant. 1.7 times sine of 40 is 1.093. Also in the third quadrant, y is also negative, so I have that. Now, if you don't like trying to remember, if you're like, well, Born, I would rather just enter a number in the calculator and make sure I get the angle, the sine of the angle is right, the plus or minus. There's another way to do that, and that is to keep in mind that 40 degrees in the third quadrant is the same as, and this is going to be important later, 180 plus the 40. So the total angle would be, let's see, 180 plus 40, that's going to be 320. 320, 220. There we go. So I could do the exact same thing. Watch this. Ready? V2x equals 1.7 times the cosine of 220. And you will get, go ahead, try it, 1.7 times cosine, whoops. And you get, guess what? Negative 1.302. So it will take care of that. In that case, you don't have to worry about remembering what it is in the third quadrant. If you use this angle, you're good to go. So it's up to you, really, but you don't want to drop a negative sign. You don't want to, mess that up. But here we have the x and y components for the vector 2 and the x and y components for vector 1. I'm going to suggest or tell you that what you want to do, well, by the way, let's go back for a second. So we have now achieved this. Check. We've broken each vector down into its components. I would say let's write them. This is kind of an important step for organization. I would say let's write those components like this. Let us write them in component form. So in other words, I am now going to write that vector 1 in component form, I write its x component first, 4.423, I'll drop the units for a second, is the x component minus 3.097 is the y component. Notice the negative here is where I get this little minus sign from, the negative sign from. Meanwhile, vector 2 is negative 1.302 is its x component, and negative 1.093 is its y component. And I would highly, 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 highly recommend that you write it just like that. The reason being, is when we go to combine these, this is going to make it a lot easier. So we can literally just draw a line, bam, and combine the x's. So I have 4.423 plus a negative 1.302, or if you just want to do minus 1.302, gets me, by the way, this is the resultant. What I get as the answer is going to be 3.121 positive, x component. And the negative, well, sorry, the y component should come out negative because both of these are negative. So I have negative 3.097 plus a negative or minus, however you want to look at it, it's going to come out the same. But you don't want to do minus a negative in this case. 93, and you're going to get negative 4.19 is your y component. So this right here, so if we had those two vectors, one was longish and down in here, and the other was short and like that, and the resultant, which was the one in purple, you might recall, was something like this. Well, this right here represents that vector, the sum of the two. But you'll recall that we want the opposite of that vector. So here's the easiest way on the face of the planet to make the opposite. The opposite of this vector right here. To get it, the easiest way is to switch the signs. Change the signs, I should say. So, for example, this is positive. You don't see it, but it's positive. Make it negative. Negative 3.121 is now your x component. And this is negative, so make it positive. Boom. So now, instead of going positive, negative to get to there, we're going to go the same amount negative, positive, and get to the exact opposite direction. So this is basically our answer, but it's in component form. And for our activity/lab, we don't want it in component form. We're going to want it in angle magnitude form. So we added them up. So we want and now we've also found the opposite. Check. We've done both of those. We combine the x's with the x's and the y's with the y's, got a resultant, got an answer, a sum of the two vectors, you might say. And then we switch the signs to get the opposite. One more step, which actually has got a couple little steps in it, and that is to put that vector in angle magnitude form. So let's do that. So we're going to start with this vector, and there's two things we need. We need, well, the magnitude of the opposite vector, how big it is, and we need the reference angle. Well, the magnitude is given by the square root of the x component squared. You can leave the negative if you like, but be careful because you don't want it, plus the y component squared, and then take the square root. So that's going to be 3.121 squared. That should come out positive because you're squaring a negative. So negative times a negative is a positive. Plus 4.19 squared equals. So I got the magnitude of the opposite vector. The one I'm looking for is going to be the square root of 27.297. Take the square root of both sides there. Well, not take the square root of both sides. Sorry. Take the square root, because that's what the equation tells me to do. And I get a magnitude for that opposite vector of 5.22 newtons. Okay. Now we need a reference angle. That's going to be the inverse tangent of the y component. Just worry about positive and negative. Just worry about the positives. Don't worry about if it's negative. Divided by the x component. That's what these vertical lines mean. So you just worry about this positive value. Don't worry about anything that's negative. Just drop negative signs. So that's going to be the inverse tangent of 4.19 divided by 3.121. So we'll try that. We'll go 4.19 divided by 3.121, and then do second tangent, and I got a 53.3 degrees. So the reference angle is 53.3 degrees. Huh, what quadrant? Well, this is where your sketch, among other things, can help. We already know from our sketch that opposite vector was pointed up here in the second quadrant. So if you trust your sketch, you just put second quadrant. But there's another way to tell. Take a look at this. You see how the x component is negative, the y component is positive? That means negative x, positive y. That tells us it's got to be the second quadrant. So there's two indicators, a good sketch and knowing how to interpret these signs. A negative x and a positive y is definitely second quadrant. So I'm going to write second quadrant. Now you could also, if you want, not give it as a reference angle. So in other words, you could write this two ways. You could say this opposite vector that we're looking for has a magnitude of 5.22 newtons at, you could write 53.3 degrees second quadrant. But I don't think that's going to work super well on this next thing because of the way that the apparatus is set up. So I would like this angle not as a reference angle. So they're telling me that I got this angle here is the 53.3. It's a reference angle, always to the x-axis. But what I really want, I believe here, is I want this angle from here to here. You got this. Do you agree with me that from here all the way over would be 180? So this green angle is simply 180 minus the 53.3. That gives us an angle of 126.7. So another way to write this is the opposite vector is 5.22 newtons at 127 degrees. And we don't have to say what quadrant, because 127 degrees is in the second quadrant. This is the way we're going to want it. The only other thing I will tell you is this. This is in the way we're going to do the lab, that's a force. In this case, actually, in the lab, it's going to be a weight. Now, we know that the weight of an object is equal to its mass times g, g being 9.8. I'm going to still use newtons per kilogram. We want the mass. We have to know how much mass to do this with. So if I wanted the mass, it's just going to be the weight divided by g. This brings up the point that in any time in physics, if you know the mass, you can find the weight. And if you're given the weight, you can find the mass. If you know one, you know the other as long as you're on Earth, because you'll know this. So in this case, 5.22 newtons divided by 9.8 newtons per kilogram is going to give me how many kilograms worth of mass. So I'm going to go 5.22 divided by 9.8, and that's going to be a mass of 0.533 kilograms, thereabouts. So that'll be a last step that you will have to do in the activity. But if you're getting to here or here, you're in pretty good shape. I recommend, let's do this. I'm going to throw out a couple of vectors here. So here's the example I want you to do. We'll call vector 1 will be 6.8 newtons at 121 degrees. Vector 2 will be 7.2 newtons at 15 degrees, fourth quadrant. So find a third vector that will cancel those two out using the steps we just outlined. I would pause the video and come back to it, and I will show you the answer. The opposite vector that will cancel out those two. And so pause the video. I'm going to double check my answer and then come back and look at it. Okay, so hopefully you haven't cheated and just let the video run. We are going to have, it should come out to be, we'll write it two ways, 5.26 newtons at 49 degrees in the third quadrant. Or an even better way to write it would be 5.26 newtons at 229 degrees. And if you needed to find the mass associated with the 5.26 newtons, you could of course go 5.26 divided by 9.8 and get the mass associated with this would be 0.537 kilograms. So there's your answer. Hopefully you got it. Check with me in the start of class if you didn't, because you're going to need to be able to do this. All right, that's it.